You're stuck in traffic, late for work, frustrated. You glance at the clock and suddenly wish you could just teleport there instantly. Or maybe you wonder, if only I could send a message faster than light. I could have warned myself to leave earlier. We've all had these moments. These everyday frustrations that make us dream of breaking the ultimate barrier, the cosmic speed limit, the speed of light. But here's what gnaws at you in the quiet moments. Here's what keeps physicists awake at night. It's not just that we can't go faster than light. It's that this limit seems to cage our understanding itself. It's as if the universe erected a wall and said, "Beyond this, you cannot know. Beyond this, reality itself breaks down." And that terrifies us. Because if there's a speed limit to information, to causality, to knowledge itself, then maybe we're trapped. Maybe our minds, our instruments, our entire civilization is locked inside a cosmic prison we can never escape. Richard Feynman understood this terror. He felt it deeply. But he also saw something else, something that most people miss. The speed of light isn't just a barrier. It's a window. It's not the limit of understanding. It's the beginning of it. And when you truly grasp what Feynman discovered about this cosmic speed limit, when you understand why it exists and what it really means, everything changes. Your view of space shatters. Your understanding of time dissolves. And you realize that the universe is far stranger, far more beautiful, and far more interconnected than you ever imagined. This isn't a story about limitation. This is a story about revelation, about how the very thing that seems to imprison us is actually the key that unlocks the deepest secrets of reality. Feynman didn't just accept the speed limit. He used it as a tool to peer into the fabric of existence itself. And what he found there will reshape how you see every moment of your life. Because once you understand why nothing can go faster than light, once you grasp what this limit really represents, you'll never look at space, time, or reality the same way again. You'll see that the cosmic speed limit isn't a bug in the universe. It's a feature. And it's the most profound feature of all. So let me ask you something. Why can't we go faster than light? And before you answer, really think about it. Don't just say Einstein proved it, or that's just how physics works. Those aren't answers. Those are labels we slap on mysteries to make ourselves feel comfortable. The real question cuts deeper. What is light speed actually limiting? Is it just motion? Is it just particles zipping through space? Or is it something far more fundamental? Here's where most explanations fail you. They tell you that as you approach light speed, your mass increases. You need infinite energy, so you can't get there. But that's circular reasoning. It's describing the symptom, not the cause. It's like saying you can't lift a mountain because it's too heavy. True, but why is it too heavy? What makes it impossible? Feynman hated this kind of shallow thinking. He would push back hard. Because the speed of light limit isn't about mass or energy. It's about the structure of space-time itself. It's about causality. It's about the very fabric of existence having a maximum rate at which cause and effect can propagate. And here's the disturbing part that nobody tells you. The speed of light isn't fast. From the universe's perspective, light speed is actually the problem. It's slow. Information crawls through space. The sun could explode right now, and you wouldn't know for 8 minutes. The nearest star could vanish, and you'd still see it for 4 years. You're always looking at the past. You're always living in delayed reality. And this delay, this fundamental sluggishness of information, isn't a limitation imposed on a perfect universe. It is the universe. The delay is the structure. The limit is the foundation. And once you understand why, everything Feynman taught about reality suddenly clicks into focus. you realize we've been asking the wrong question all along. In the summer of 1905, a patent clerk in Switzerland was thinking about trains. Not because he loved trains, but because he was obsessed with a problem that had haunted physics for decades. How do you know when two events happen at the same time? Imagine you're standing on a train platform. A train rushes past you at tremendous speed. Lightning strikes both ends of the train simultaneously from your perspective. The flashes reach your eyes at the same instant. But here's the question that changed everything. Does a passenger in the middle of the train see the same thing? Albert Einstein realized the answer was no. The passenger is moving toward one flash and away from the other. The light from the front of the train reaches them before the light from the back. To the passenger, the lightning strikes don't happen simultaneously. They happen at different times. This seems like a minor detail, a peculiarity of perception. But Einstein saw deeper. He realized this wasn't about perception. It was about reality itself. There is no absolute simultaneity. Events that are simultaneous for you are not simultaneous for someone moving relative to you. Time itself is not universal. It's observer-dependent. And the key, the absolute linchpin of this entire revolution, was one simple fact that Einstein took as a fundamental postulate. The speed of light is the same for everyone, regardless of how they're moving. You're on a train moving at half the speed of light, you shine a flashlight forward, the light doesn't go at 1.5 times light speed. It still goes at exactly light speed. You're moving toward a light source at tremendous velocity. The light doesn't appear faster to you. It's still exactly light speed. This seemed impossible. It violated every intuition about how motion should work. But experiment after experiment confirmed it. The Michelson-Morley experiment in 1887 had already shown that light speed doesn't change no matter how you're moving through space. Einstein took this experimental fact and built an entire new physics from it. He showed that if light speed is constant for all observers, then time and space must be flexible. They must stretch and compress to keep light speed fixed. When you move fast, time slows down for you. Distances shrink, mass increases. All of reality warps around you to preserve one sacred constant, the speed of light at roughly 299,792, 458 meters per second. But why? Why should the universe care so much about this particular speed? Why build all of space-time around preserving it? This is where most physics courses stop. They give you the equations. They show you time dilation and length contraction. They demonstrate relativistic mass. But they don't tell you why. They don't explain what light speed really is. Now, before we go deeper into why light speed is what it is, I want to hear from you. Because here's something Feynman always emphasized. Understanding physics isn't about memorizing facts. It's about wrestling with ideas. It's about asking questions that challenge your intuitions. So tell me in the comments, what do you think light speed actually limits? Do you think it's just about motion, about particles moving through space? Or do you think it's something deeper, something about information, about how cause and effect work, about the structure of reality itself? And here's a tougher question. If we could somehow go faster than light, what do you think would happen? Would we just arrive somewhere quickly? Or would we break something fundamental about how the universe operates? Would we violate causality itself? Share your thoughts below, because understanding where your intuition leads you is the first step to understanding where Feynman's reasoning will take you. And trust me, where we're going next is somewhere your intuition has probably never been before. Drop your answer in the comments right now. Let's see how many of you can guess what Feynman understood about the true nature of this cosmic speed limit. I'll tell you this much, it's not what you think. Richard Feynman approached the speed of light from a completely different angle. While other physicists were focused on special relativity, On the geometry of spacetime, Feynman was thinking about quantum mechanics, about photons, about how light actually behaves at the deepest level. And what he discovered was extraordinary. The speed of light isn't a speed limit in the traditional sense. It's the speed at which causality propagates. It's the maximum rate at which cause and effect can be linked. Let me explain what this means. In Feynman's quantum electrodynamics, light isn't just a wave or a particle. It's an excitation in the electromagnetic field. And this field permeates all of space. It's everywhere, always. When you flip a light switch, you don't create light that travels from the bulb to your eye. You disturb the electromagnetic field, and that disturbance propagates outward at light speed. The photon you detect isn't a little ball that traveled from A to B. It's a quantum of energy transfer in the field. Now here's the crucial insight. The electromagnetic field, like all fundamental fields in physics, has a property called the propagator. This describes how disturbances in the field spread through spacetime. And Feynman's calculations showed something remarkable. The propagator has a maximum speed. Information about a disturbance at one point cannot affect another point faster than this maximum speed. For the electromagnetic field, that speed is exactly the speed of light. But here's where it gets mind-bending. This isn't special to light. All massless particles, anything with no rest mass, must travel at exactly this speed. Photons do it, gluons do it, gravitational waves do it, and massive particles, things with rest mass like electrons or protons, must travel slower than this speed. Not because something is holding them back, but because the structure of spacetime itself only allows one speed for massless information transfer. Feynman showed that this speed, what we call the speed of light, is really the speed of causality. It's the speed at which one event can influence another. And here's the truly strange part. This speed isn't a property of light. Light just happens to travel at this speed because photons have no mass. The fundamental constant is the speed of causality, often called c in physics equations. Light speed is just a convenient way to measure it because light is easy to detect and measure. So when we say nothing can go faster than light, what we really mean is nothing can go faster than the maximum speed of causality. Nothing can influence something else faster than this fundamental limit. And this limit emerges from the very structure of spacetime. It's baked into the geometry of the universe itself. Now, let's get even deeper. In special relativity, spacetime is described by a mathematical structure called the Minkowski metric. This metric has a peculiar property. It treats time differently from space. Space dimensions have positive signs in the metric. Time has a negative sign. This creates a fundamental asymmetry, and from this asymmetry, a natural speed emerges. A speed that converts between space and time units. A speed that defines the structure of light cones, the regions of spacetime that can be causally connected. This speed is c, the speed of light, the speed of causality. And here's what Feynman understood better than almost anyone. This speed isn't a barrier keeping us out. It's a scaffold holding reality together. Without this limit, causality would break down. Effects could precede causes. The universe would be chaos. The past could influence itself. Paradoxes would be everywhere. The speed of light is the universe's way of keeping time ordered, of ensuring that cause comes before effect, of maintaining logical consistency in the flow of events. Feynman often illustrated this with thought experiments. Imagine you could send a signal faster than light. You send it to someone moving relative to you. From their reference frame, because of relativity's rules, that signal arrives before it was sent. They send a signal back to you, also faster than light. And from your reference frame, their return signal arrives before you sent your original signal. You've received a message from the future. You can now prevent yourself from sending the original message. You've created a paradox. You've broken causality. This isn't science fiction speculation. This is rigorous physics. If faster-than-light travel were possible, time travel into the past would be possible. And not in some exotic way involving black holes or wormholes, just by having two objects in relative motion and faster-than-light communication between them. The equations are clear. Faster than light means time travel. Time travel means paradox. Paradox means the logical structure of the universe falls apart. So the speed of light isn't arbitrary. It's not a cosmic speed limit sign that some celestial traffic cop put up. It's the fundamental rate at which the universe can remain logically consistent. It's the price of causality. It's the speed at which reality holds together. This understanding leads to profound implications that ripple through every corner of physics and technology. First, consider GPS satellites. These devices orbiting Earth at about 20,000 kilometers altitude are moving at roughly 14,000 kilometers per hour relative to the ground. Not particularly fast by cosmic standards, but relativistic effects are measurable. Einstein's special relativity predicts that the satellite clocks run slower than ground clocks due to their motion, about 7 microseconds per day slower. But general relativity adds another effect. The satellites are in a weaker gravitational field than the surface, so their clocks run faster, about 45 microseconds per day faster. The net effect is about 38 microseconds per day fast compared to ground clocks. That seems tiny, but light travels about 300 meters per microsecond. Without correcting for relativity, GPS would accumulate position errors of over 10 kilometers per day. Your navigation would be useless. The entire system works only because engineers account for the speed of light limit and how it warps time. Every time you use GPS, you're experiencing Feynman's insight about causality and light speed made practical. Second, particle accelerators. At CERN's Large Hadron Collider, protons are accelerated to 99.99991% of light speed. At these velocities, the protons aren't just fast. Their mass increases by a factor of over 7,000. They carry enormous kinetic energy, about 5 trillion electron volts per proton. But no matter how much energy you pump in, they never quite reach light speed. As you approach c, each additional bit of energy adds less and less velocity and more mass. The energy requirements approach infinity as velocity approaches light speed. This isn't a technological limitation. It's a fundamental property of space-time. The accelerator is pushing against the structure of the universe itself, and experiments have confirmed this to extraordinary precision. The proton behavior matches relativistic predictions to better than 1 part in a billion. The speed of light limit isn't theory, it's measured reality. Third, cosmology. When we look at distant galaxies, we see them not as they are, but as they were billions of years ago. The Hubble Space Telescope's deep field images show galaxies over 13 billion light-years away. We're seeing them as they appeared when the universe was less than 1 billion years old. These galaxies are so distant that space itself has expanded significantly since the light left them. The current distance to these galaxies is actually greater than 13 billion light-years, perhaps over 45 billion light-years, due to expansion. But the light still took over 13 billion years to reach us, because it's limited by light speed, by causality speed. This means there's a cosmic horizon. There are parts of the universe so far away that light from them hasn't had time to reach us yet. Not because space blocks it, but because the universe has a finite age, and information propagates at finite speed. The observable universe has a boundary not of space, but of time. Beyond that boundary, events haven't yet had causal influence on us. We are informationally isolated from those regions. And here's the eerie part. As the universe continues to expand and accelerate in its expansion due to dark energy, this horizon will actually shrink in a sense. Galaxies that we can see now will eventually accelerate away from us faster than light, not because they're moving through space that fast, but because space between us and them is expanding. Their light will no longer reach us. They will fade from view. Entire galaxies will disappear from our observable universe. The speed of light limit combined with cosmic expansion creates an ever-shrinking window of what we can observe and influence. Fourth, quantum entanglement. This is where things get truly strange. Feynman was deeply involved in understanding quantum mechanics, and one of its most bizarre features is entanglement. Two particles can be prepared in a quantum state such that measuring one instantly affects the other, no matter how far apart they are. Measure the spin of one electron, and you instantly know the spin of its entangled partner, even if it's on the other side of the galaxy. This seems to violate the light speed limit. Information appears to travel instantaneously. Einstein called it spooky action at a distance and believed it proved quantum mechanics was incomplete. But Feynman and others showed that entanglement doesn't actually allow faster-than-light communication. Yes, the correlation between particles is instantaneous, but you can't use this to send a message. You can't control what result you get when you measure your particle. And the person measuring the other particle sees only random results until they compare notes with you through normal, slower-than-light communication. Entanglement preserves correlations faster than light, but it doesn't transmit information faster than light. Causality is safe. The light speed limit holds. But this reveals something profound about reality. Quantum correlations exist outside the normal flow of space-time causality. The universe has non-local connections built into its quantum foundation. Space doesn't separate entangled particles in the way we normally think of separation. And yet, paradoxically, these non-local connections can't be used to send signals, can't be used to violate causality. It's as if the universe is correlated in ways that transcend space, but still respects the causal structure that light speed enforces. Feynman spent much of his career trying to understand this tension between quantum non-locality and relativistic causality. His path-integral formulation of quantum mechanics was partly an attempt to reconcile these seemingly contradictory features of reality. And what he found was that the universe is far more interconnected, far more holistic than our everyday experience suggests, but that this interconnection is carefully balanced to never violate the causal order that makes time and logic possible. If you're finding this mind expanding, if you're starting to see light speed not as a barrier but as a window into deeper reality, do me a favor. Hit that like button and subscribe to the channel, because we're going even deeper into how this cosmic speed limit reveals truths about existence that most people never encounter. Understanding Feynman's perspective on light speed is just the beginning of understanding how strange and beautiful the universe really is. So we've established that the speed of light is really the speed of causality, the maximum rate at which cause can lead to effect. But now we need to ask the ultimate question. Why this particular speed? Why 299, 792, 458 meters per second, and not some other value? Why isn't causality instantaneous? Why does information have to crawl through space at all? This is where Feynman's deepest insights come in. And to understand them, we need to think about what space and time actually are. In Newtonian physics, space was absolute, a rigid stage on which events occurred. Time was absolute too, flowing uniformly everywhere. But Einstein destroyed this picture. Space and time aren't separate entities. They're woven together into space-time, a four-dimensional fabric that can bend, stretch, and curve. And the speed of light is the conversion factor between space and time dimensions. It's the exchange rate between meters and seconds. Why do we need an exchange rate? because space and time are fundamentally different types of dimensions, but they're part of the same geometric structure. The speed of light, c, is the constant that makes the units compatible. In fact, many physicists prefer to work in units where CEE equals 1, where we measure time in meters or distance in seconds. In these natural units, the speed of light isn't a speed at all. It's just the number 1. It's the fundamental ratio that defines how space-time works. Now here's the profound part. The value of tau, the speed of light, is related to the structure of the electromagnetic field. Specifically, it emerges from two constants, the permittivity of free space and the permeability of free space. These constants describe how electric and magnetic fields propagate through vacuum. And when James Clerk Maxwell worked out his equations of electromagnetism in the 1860s, he found that electromagnetic waves must propagate at a speed equal to 1 divided by the square root of permittivity times permeability. When he calculated this speed using measured values of permittivity and permeability, he got roughly 300,000 kilometers per second, the same as the measured speed of light. This was one of the greatest revelations in physics history. Light is an electromagnetic wave, and its speed is determined by the properties of the electromagnetic field itself. But this just pushes the question back. Why do permittivity and permeability have the values they do? Feynman would tell you that this is where we hit the boundary of current understanding. In our present theories, these constants are fundamental. They're inputs to the theory, not outputs. We measure them. We don't derive them from deeper principles. Some physicists hope that a future theory of everything might explain why these constants have their particular values. Perhaps they're determined by the geometry of extra dimensions, or by quantum gravity, or by some principle we haven't discovered yet. But right now, we accept them as given. The universe has these properties, and from them, the speed of light emerges. However, Feynman did have a perspective on why there should be a finite speed at all, why causality isn't instantaneous. It comes from the quantum nature of fields. In quantum field theory, which Feynman helped create, particles are excitations of fields, and fields have uncertainty built into them. You cannot know the exact value of a field at a precise point in space-time and also know how it's changing. There's a Heisenberg uncertainty principle for fields, just as there is for particles. This uncertainty has profound consequences. It means that a field disturbance at one point takes time to manifest at another point. The information about the disturbance has to propagate through the uncertain quantum fluctuations of the field. And there's a maximum rate at which this can happen without violating the uncertainty principle. That maximum rate is the speed of light for massless fields. Feynman showed that if you try to make information propagate faster than light in quantum field theory, you get nonsensical results. Probabilities become negative. You get answers that violate causality. The math itself breaks down. The theory is telling you that faster-than-light propagation is not just forbidden by law. It's logically incoherent. It's not that the universe prohibits it. It's that faster-than-light doesn't mean anything. It's like asking what's north of the North Pole. The question itself doesn't make sense once you understand the geometry involved. And this brings us to perhaps Feynman's most profound insight about the speed of light. The limit isn't constraining us. It's defining what existence means. Without a finite speed of causality, without light speed being finite, the concepts of here and there, now and then, cause and effect would have no meaning. Reality would be an atemporal block where everything influences everything else instantaneously. There would be no flow of time, no history, no narrative of events. There would be no way to separate cause from effect. The universe would be, in a sense, timeless and structureless. The speed of light creates time. It creates separation. It creates the possibility of independent events. of things happening in sequence, of cause preceding effect. It creates the space in which complexity can grow, in which information can accumulate, in which life and consciousness can emerge. Think about it this way. If information could travel infinitely fast, if causality were instantaneous, then every part of the universe would be instantly correlated with every other part. There would be no local structures, no isolated systems, no way for complexity to build up in one region without instantly spreading everywhere. The universe would be homogeneous, boring, dead. The finite speed of light creates islands of causality. It creates regions of space-time that can evolve independently for a while before interacting. It allows for diversity, for structure, for the rich tapestry of phenomena we observe. Without the speed limit, none of this would exist. You wouldn't exist. The neurons in your brain communicate through chemical and electrical signals that take time to propagate. If those signals were instantaneous, if there were no causal structure to their firing patterns, there would be no thought, no experience, no consciousness. The speed of light, by being finite, by creating temporal structure, makes consciousness possible. It makes existence possible. And here we arrive at what might be Feynman's ultimate answer to the question, is the speed of light the limit of our understanding? The answer is no. Absolutely not. The speed of light is not a barrier to understanding. It's a gateway. It's the very thing that makes understanding possible. Because understanding requires structure. It requires one thought to build on another, requires cause and effect, requires time for information to be processed and integrated. All of this depends on causality having a finite speed. If light speed were infinite, if causality were instantaneous, there would be nothing to understand because there would be no structure to reality. Everything would be everything else. There would be no distinctions, no patterns, no laws of physics to discover. The fact that light speed is finite, that causality propagates at a limited rate, is what creates the universe we can explore, measure, and comprehend. Every discovery in physics, every equation, every experiment, every insight exists only because causality has a finite speed. The speed of light doesn't limit understanding, it enables it. And recognizing this, truly grasping it, changes everything. You stop seeing the cosmic speed limit as a frustration, as a barrier keeping you from exploring the universe instantly. You start seeing it as the fundamental principle that allows the universe to exist, in a form you can explore at all. You realize that the delay in light reaching your eyes from distant stars isn't a bug. It's a feature. It means those stars have a history, that the light carries information about where it came from, about what happened there millions of years ago. That information exists because causality is finite. You understand that the fact you can only influence events within your future light cone, the region of space-time that light from your position can reach, isn't a limitation. It's the definition of what it means for you to exist as a distinct entity with agency. Your ability to make choices, to have an effect on the world, depends entirely on there being a boundary to your causal influence. Without that boundary, the concept of you as an individual agent makes no sense. Feynman saw all of this. He saw that the equations of physics, the speed of light constant appearing everywhere, wasn't just a random number. It was the signature of causality, the mark of temporal structure, the fingerprint of existence itself. And he devoted his life to exploring what this means, to pushing the boundaries of how we understand causality, field theory, quantum mechanics, space-time. He showed that the speed limit isn't where our understanding ends, it's where our understanding begins. Because once you know why light speed is what it is, once you grasp that it's the speed of causality, the rate at which the universe maintains logical coherence, you suddenly have a tool to probe deeper questions. You can ask, what happens at light speed itself? What is it like to be a photon? The answer is strange. A photon experiences no time. From its perspective, emission and absorption happen in the same instant. It crosses billions of light-years of space in zero subjective time. Time exists only for things moving slower than light. For massive particles, for observers who cannot reach light speed. Light itself exists at the boundary where time ceases. You can ask, what happens when space-time curves dramatically? Like near a black hole? The speed of light stays constant locally, but the geometry of space-time warps so severely that light itself can be trapped, unable to escape the event horizon. The speed limit is still there, still enforced, but the arena in which it operates is bent into configurations we can barely imagine. You can ask, what happened in the earliest moments of the universe, when space-time itself was emerging from the quantum foam? How did causality get established? How did light speed become defined? These questions take us to the frontiers of quantum gravity, of theories like string theory and loop quantum gravity, where space-time itself might be quantized, where the smooth fabric we experience emerges from discrete quantum building blocks. And the speed of light, the speed of causality, might be a thermodynamic property of this quantum space-time, similar to how the speed of sound is a property of the material it travels through. Feynman would be thrilled by these questions. He thrived on the boundary between known and unknown, between what we can calculate and what remains mysterious. And he always emphasized that the most important skill in physics is not knowing the answer, it's knowing how to think about the question. The speed of light teaches us how to think. It teaches us that reality has structure, that structure has limits, and that those limits are not walls, they're foundations. They're the ground on which all understanding is built. So no, the speed of light is not the limit of our understanding. It's the key to it. It's the constant that appears in every equation describing how information flows, how fields interact, how particles behave. It's the thread connecting electromagnetism to special relativity, to quantum field theory, to general relativity. It's the number that, more than any other, defines what it means for anything to exist. And when you truly internalize this, when you feel it in your bones the way Feynman did, the universe opens up. You stop being frustrated by what you can't do and start being awed by what is. You see a cosmic speed limit and recognize it as a cosmic foundation. You look at distant galaxies billions of light-years away and see not separation, but connection. Information traveling to you at exactly the speed it must to preserve causality, to maintain the logical structure that makes both you and the galaxy real. You understand that every photon entering your eye, every signal reaching your instruments, every piece of information you've ever received has traveled at light speed, at causality speed, at the fundamental rate of existence. And that makes every observation a miracle, every measurement a glimpse into the deep structure of space-time. The speed of light isn't limiting you. It's connecting you to everything that can be connected, to everything that shares your causal future or past. And beyond your light cone, beyond the boundary that light defines, there are other regions of space-time equally real, equally structured by the same cosmic speed limit. Not cut off from you permanently, but simply not yet in causal contact. Given time, given the expansion or contraction of the universe, those regions may enter your light cone or leave it. But wherever they are, whatever happens there, the same speed of causality holds, the same laws govern, the same fundamental structure persists. This is what Feynman meant when he said that the glory of physics is understanding not just what happens, but why it must happen the way it does. The speed of light must be finite. Causality must propagate at a limited rate. Time must flow. Space must separate. Effects must follow causes. Not because nature chose these rules arbitrarily, But because these properties are what it means for a coherent, structured universe to exist at all, and we are part of that universe. We are patterns in space-time, configurations of matter and energy that persist because causal structure allows complexity to accumulate. Our thoughts are causal chains. Our memories are records of past light cones. Our plans are attempts to influence future ones. Everything we are depends on the speed of light being exactly what it is. So when you feel frustrated by the cosmic speed limit, when you wish you could travel to distant stars instantly, when you dream of faster-than-light communication, remember Feynman's insight. That wish is like wishing you could exist without existing, like wanting to think without time, like hoping to be conscious without causality. The speed limit is not your enemy. It's your foundation. It's the reason you're here to ask the question at all. And that, perhaps, is the most mind-blowing thing of all.